Welcome back, everyone, to another explainer. Today, we're getting into something absolutely crucial. We're talking about the literal backbone of our global energy infrastructure, API Specification 5L. We're going to completely dissect the anatomy of pipeline integrity, going all the way from intense physical stress tests right down to the actual atomic recipe of the steel itself. Let's get into it.
So think about this massive engineering question for a second. How exactly do we guarantee a steel pipeline won't just snap right in half when it's submerged deep under the ocean? I mean, we're talking freezing temperatures, crushing pressures, and highly corrosive environments. In these situations, failure literally is not an option. The margin for error? Zero. So to hit that incredible standard, engineers rely on some astonishingly precise testing methodologies to validate every single millimeter of that steel before it ever leaves the mill.
All right, to understand exactly how this standard guarantees that safety, we're going to walk through 5 phases. First, mechanical and hardness testing. Second, non-destructive inspection. Third, standards for welded joiners. Fourth, engineering for extreme strain. And finally, chemical composition and designations.
Okay, starting off with phase 1, mechanical and hardness testing.
To really prove a pipeline's strength, engineers actually have to destroy some of it. It's called destructive testing. Basically, they take sample pieces and push the metal to its absolute limits until it physically breaks. During these tests, specific tiny X marks are mapped out across the arc of the weld. Those aren't random. API 5L strictly dictates the exact, non-negotiable locations where hardness has to be measured, both right on the weld itself and on the surrounding parent metal.
The level of precision required here is just fascinating. Step 1, testers have to indent the exact weld center line. Step 2, they move precisely 0.75 millimeters into the parent metal. And step 3, they test at exactly 1.0 millimeter spacing all throughout the visible heat-affected zone. It might sound like a bunch of abstract rules, but this standard forces an incredibly thorough investigation into a notorious hotspot for potential brittle fractures.
Now, while destructive testing is great for verifying the manufacturing process on sample batches, verifying the final service-ready product requires a completely different approach. Obviously, we can't break the pipe we're actually going to put in the ground. So we transition from breaking samples to non-destructive inspection, or NDT. This is where we use things like ultrasonic waves and magnetic fields to validate the finished pipes.
Which brings us nicely to phase 2, non-destructive inspection. You can think of NDT kind of like a super advanced medical ultrasound, but for steel. The equipment is primarily hunting for what we call laminar imperfections. These are basically internal separations hidden deep inside that solid steel wall. The standard specifically defines this as a defect if it extends more than 6.4 millimeters circumferentially, or if the total area of the flaw exceeds 100 square millimeters at the pipe ends. If the equipment pings a flaw even that tiny, boom, that section of pipe is immediately rejected. No questions asked.
And what's really interesting is that these acceptance criteria adapt heavily based on where the pipe is actually going to be used. For a standard offshore pipe body, an internal imperfection can reach a maximum area of 1,000 square millimeters before it's officially classified as a defect. But if you're dealing with sour service conditions, which means highly corrosive environments, that tolerance gets slashed in half down to 500 square millimeters. Basically, the more dangerous the environment, the tighter the margins become for even microscopic flaws.
So to make sure absolutely zero critical flaws slip through, the standard mandates an intense, and I mean intense, battery of NDT methods. We're talking full-body ultrasonic inspections just to catch longitudinal cracks. They use magnetic particle inspection precisely at the pipe ends and bevels. If it's a seamless pipe, they use the flux leakage method to detect transverse flaws. And for that sour surface we just mentioned, they mandate a 100% inspection of the plate surfaces to detect surface hard layers. They literally leave nothing to chance.
Moving right along to phase 3, standards for welded joiners.
Now, pipes usually come out of the mill in standard length, right? But when a project site needs a much longer section, they have to join 2 pipes together, which introduces a whole new set of variables. The rules for these joiners are incredibly strict to prevent any weak points. For instance, they require destructive testing on at least 1 out of every 100 welded joiners. And when you're joining pipes that have longitudinal weld seams, those seams actually have to have a circumferential separation of between 50 and 200 millimeters. On top of that, geometrically speaking, these massive pipe sections cannot be offset by more than 3.2 millimeters where they connect. It's like a giant, high-stakes puzzle. But doing the physical welding is really only half the battle. The other half? Meticulous traceability.
Every single segment of a joiner has to be explicitly marked. We're talking permanent stencils like Joint A, and Joint B, Heat B. This ensures that if a flaw is discovered, say 5 years down the line, engineers can trace the exact batch of steel and even the specific welding operator straight back to the factory. It's built-in accountability.
Okay, phase 4, engineering for extreme strain. Standard pipelines are mostly designed to withstand internal pressure. But what happens when you cross an active seismic fault line, or shifting permafrost, or install pipes in ultra-deep water? That requires a completely different class of pipe. We measure this specialized metallurgy by its longitudinal plastic strain capacity. Basically, this pipe is engineered to safely stretch and bend under strains greater than 0.5% without a catastrophic failure. And to pull that off, it requires what's called fully killed steel and incredibly clean steel-making practices to guarantee maximum toughness. And that brings us to our final phase, phase 5, chemical composition and designations. So the crucial takeaway here is that everything we've talked about, from hardness to crack resistance to the ability to bend without snapping, is ultimately dictated by the steel's atomic recipe. And because oil and gas is a truly global industry, API 5L acts as this universal language. For example, an API grade L415 maps directly over to the European steel number 1.8725. This ensures that an engineer sitting in Houston and a fabricator working in Rotterdam are perfectly aligned on the exact same material capabilities. Now, getting those material capabilities right comes down to a highly specific, closely guarded recipe. It's all about the precise mass fractions of elements like carbon, manganese, phosphorus, sulfur, and vital microalloys like niobium, vanadium, and titanium. Adjusting any of these elements by even a tiny fraction of a percent completely changes how that steel is going to behave under stress. To put into perspective just how precise this has to be, let's look at the number 0.17%. That tiny fraction is the absolute maximum allowable carbon mass fraction for high-strength, extreme-strain pipe grades like X80. If you add too much carbon, the steel becomes way too brittle and won't bend. But if you have too little, it loses its structural strength. So pipeline engineers are effectively custom-baking this steel at a molecular level just to perfectly balance strength and flexibility. They are literally preventing environmental disasters before they even have a chance to happen. From pounding a weld with a hardness tester to balancing microalloys down to a fraction of a single percent, the anatomy of pipeline integrity really is a masterclass in risk management. But it definitely leaves us with a provocative question to chew on. As global energy demands inevitably push our pipelines into even deeper waters, higher pressures, and incredibly harsh Arctic environments, how are these standards and the material science behind them going to evolve to conquer the next frontier of extreme engineering? It's something to think about. Thanks for joining me on this explainer, and we'll see you next time.